This one, right? It's visible.
Yeah.
Yeah, it's right.
Perfect. So I would like to start with a presentation. So yep. So we will be looking and digging a few topics in the uh, course of data conversion. And data conversion itself is a very vast topic, but we will try to cover as much as the concepts we can cover, which we will require for the subject in our lab. So there are prerequisite, as I told. Um, So the thing is, the prerequisites are basically from all our bachelor courses, and we have network theory. We will need a few concepts from network theory. We will need few concepts from control systems. We will also require the knowledge of analog circuit design, and we will also be looking few concepts from digital signal processing. And like these are our toolboxes, and while designing a system or while designing circuits for data conversions, we will require like all the tools from these toolboxes. So whenever I'll refer to the toolbox of, let's say, control systems, so whenever we are designing a system and we are looking for feedback, let's say, so we are using a tool from a toolkit of control systems. So we will cover all those concepts as well whenever we will need them. So the contents are basically, we'll start by scratch. We'll start from introduction to the data conversion, and right from sampling or the behavior, right from noise. So we will dig deeper and we'll go deeper into it, illustrating and elaborating, and we'll target to go till higher order delta sigma modulators. And we will also look the intuitions and trade-offs while designing them. And anyway, we will be going to design them on a CMOS level. So we also have IIC, OSIC tools, right? We will be using, I guess, Skywater 130 nanometer technology. So for that, let's first build up the basics and let's start. So you can pause the screen and look all the contents. So we will try to cover all these concepts throughout the course, and we'll start with the course. So please give me a heads up if the notes are visible.
Yeah, they are visible.
Perfect. So I would like to start by laying an idea of a system or the area of system where we are trying to work on. So basically, if we imagine some system sort of,
Hello, Rishi. Sorry to interrupt.
yeah,
Can
yeah,
you hear?
yeah, Peter.
So firstly, like before starting, I wanted to know the updates about the meeting what which happened yesterday. I was not present, so can I know the updates like what was discussed yesterday and from where are we like continue?
No, this is like we will start. This is our first lecture video only. So
Okay,
yesterday we covered few things like we figured out how to record, or we figured out the way of communicating, and we figured out how to share the notes, or like how to explain the presentation. So nothing as of now is covered. So I think we are good to go.
sure, okay, okay, sure. Thanks.
Yeah, perfect. So, as I said, if we imagine a system, kind of system where we have two domains, so basically we'll always talk about two domains, digital and signal. So we have all, like everywhere, we are always available with analog signals. So whatever signal we have, be it at the sensor end or be it at the actuator end. So as we all know that actuator is basically converting electrical signals into physical forms such as heat, pressure, or the audio. and which is actually analog in domain, which we can sense again. So we have voice signals, RF signals, pressure signals, temperature signals. So these are all the analog inputs. But as of now, even though the signals are analog in nature, we want to store and process them digitally. So even though everything is analog, but we want to work on the digital world. So we need some kind of area of expertise where we can convert these analog signals into a digital domain so that we can work on them. So once the data is processed, for example, amplifying or decoding or the filtering. So let's say we converted the analog data into digital data, but now after processing or like whatever task we have to do with the data, we need to be able to, uh, for example, let's say we have our data over here and we have processed the data. So we need to be able to produce an output, which again is analog in nature. So basically, while talking about analog domain, the signals are either of sensors or the actuators. They are continuous in time as well as continuous in amplitude. So what do I mean by continuous in time and continuous in amplitude? So maybe
Okay.
nice. So let's say we will always talk about uh, amplitude, and we will always talk about time, right? So this is our amplitude and this is our time axis. So whenever we talk about analog signals, we have some sort of signals which is continuous in time and continuous in amplitude. So what do we mean by that? So this is the time, right? So whenever we talk about time, let's say at time t equals to this. So at this value of time, our amplitude might be, let's say, 5, but we can be more precise. We can say 5.1, or maybe we can say 5.1.2, or we can say 5.1.3. Like we can go to n number of decimals. So basically the amplitude is also infinite. So what am I exactly going to demonstrate is, so when we are going from analog domain to digital domain, so we will quantize time as well as we will quantize amplitude. So basically what we will do is, so when we quantize time, so let's say that's how we are quantizing the time. So first we had a signal like this, right? But now, if we say at what particular time, so at we have quantized time, we have quantized amplitude as well. So when we quantize it, it is better to make it discretize, and this is what I am talking about when I say discretizing of time or discretizing of amplitude. So let's go back to our presentation, and yeah, so the screen is visible, right?
Yeah.
Yes, right.
Perfect. So what we are trying to do is, as far as the digital domain is concerned, not only the time is quantized because of the nature of the clock. So uh, because we are only interested in the values of the signal at the edges of the clock, basically. But amplitude is also quantized because we have a register with finite number of bits. So which means that if we have n bits of register, we can only represent 2 to the power n levels. I'm talking about a digital system. So over here, so in analog domain, we have continuous amplitude and continuous time. But in digital domain, for a particular amount of time, what is the amplitude? So we can assign the value of levels. So what am I exactly talking about is that we have to discretize time as well as amplitude. So we are always playing with two factors when we are converting the data, and while discretizing them or quantizing them, we need a minimum amount of data loss. So we'll look into it. It's just an introduction. So our main focus will be on interface electronics, which lies over here, and which interfaces between the sensors and the digital state machine. On input side and on the output side, it's between the digital state machine and the actuators. So it is from analog to digital and from digital to again analog. So basically, while talking about system or interface block, which consists of firstly data conversion, as we are converting from analog to digital, but along with that, let's say we have some sort of signals which are very low and very small, that they cannot drive the whole system. So in order to drive the system, they need to be amplified. So power amplification in order to drive subsequent stages is also a factor which we need to include in this interfacing blocks. So to be very specific, we will be working in this block where our main target is to develop delta sigma modulator or the ADC. So while going from continuous time and continuous amplitude, so now,
Sorry to interrupt. I have a question.
yeah, please.
Should I write my question down and after the
Yes,
presentation ask, or I can interrupt you? But
it would be better if you write, like note down the question and then ask in the end.
okay, then I will ask in it. And
Yeah,
sorry to
perfect,
interrupt.
perfect. So we'll look into it. I am just giving a brief explanation or brief idea uh, for what we are trying to achieve. So let's say we have this domain over here, which is continuous in time and continuous in amplitude. So from this level or from analog level, we have to go to digital level. So what does a digital level means? So our time is discretized and our amplitude is also discrete. So we'll figure out how to do that. But basically, one might think that first we need to quantize time, because what we have in analog domain is continuous time and continuous amplitude. So we will first quantize time, and now some sort of confusion comes into picture that what does quantization means. So basically, quantization of time means sampling. So whenever we are talking about time and whenever we are going from analog to digital domain, so we do sampling for time, and that's called quantization of time. So first we quantize time, meaning that converting to discrete time, but amplitude is continuous at this moment. And this operation is called basically sampling, where we go from continuous to discrete time. But we can quantize the signal to the discrete amplitude after sampling. So here comes the quantization of signal. So when I talk about sampling, we quantize the time, and now our time is discrete, but the amplitude is not. So we quantize the amplitude as well to achieve discrete amplitude. So how to do that? We'll figure it out. So when we have sampled the time, the number of levels of amplitude is still infinity. It is still continuous. And the moment we quantize the amplitude, we have finite number of levels for amplitude. And once we have finite number of levels, it is possible to assign a unique digital word to each level. So let's say we have the resolution of 4 bits. So we have 2 to the power 4 bits we can assign. So we can assign the levels, and we can assign each word, digital word. What is digital word? It's basically 1010, whatever. So we can assign it to that level of that amplitude. And based on that resolution, we can increase the number of levels. So while quantization of amplitude, so if we have larger number of levels, which means we need a larger length of digital word, basically, which is in one or zeros, so which will represent the number of levels. So if we have larger number of levels, we will like, for example, we have 10 levels. So to represent 10, we need more number of bits, but we have only 4 levels. So we will require less number of bits in digital system. So that's all about like digital discretization. But in order to do this, in order to achieve a digital state from analog state, basically from here to here, uh, with minimum information loss, we need to perform quantization of time as well as amplitude. So let's talk about the quantization of time, which is sampling. So when we talk about sampling, so what we are going to do while we say we are going to sample, so basically we will analyze first. We will realize sampling methods mathematically. So there are several methods to do sampling, and we will realize them first mathematically. Then we will go on circuit level, which where we will perform the operation of sampling. And after going on circuit level, we need to prove our maths, like whatever we found out that our system will behave in a certain manner mathematically. But then while implementing it on circuits, we not only should know the mathematics while designing, but we also should consider the non-idealities occur due to the circuit elements, which deviates the results from obtained from the maths. So what do I mean by non-idealities? So for example, we need to integrate a signal, so we use a capacitor. So but a capacitor always comes with its own non-idealities. And let's say we are using a resistor, or let's say we have a circuit where we have different nodes. So from each node to the ground, there will exist a parasitic capacitance. So these are the non-idealities which introduces delays, instabilities. So this should be also taken care of. So that's how we'll go further while talking about a system or designing a system. So after sampling, we will move to quantization. So here quantization means, I mean the quantization of amplitude, because as we decided the flow. So after sampling, we will talk about quantization. So now we talked something about levels over here. So what do I mean by levels is basically, now we have a signal which is like this. So even though the time is discretized, but the signal or the amplitude is still continuous. So what we'll do is, like, let's say at particular instance of time, what is the value of that amplitude? So it can take any value between the amplitude range. Let's say it's from +5 to -5. So between +5 and -5, it can take any value. So it is like the possibility is infinity. So it's continuous. But then what we do is that if we decide that let's take a resolution of 2 to the power 2. So we have 4 bits. So then we have 4 levels, or let's say we have 5 levels. So then at this particular amount of time, the value lies between this level or this bin. So basically we have 5 bins going from 1 to 5. So we will then discretize it, that at how many volts is it. So that's how we discretize the amplitude. And there are many ways to do so. So one of the way can be comparing the input simultaneously with the thresholds. So these are the thresholds. Like we need to know now that we have to assign the value to that amplitude at that particular time, that how much is that amplitude. So instead of going to a continuous range in digital system, we will be like, we have assigned 5 values. So out of those 5 values, whatever the value or range of or value of that amplitude contains, which are it fits in, that will be represented like this. For example, our signal lies between 3 to 4 volts. So it comes between the bin or the level which is assigned over here at the 4th level. So basically to do so, we can do parallelly, we can provide a set of comparators. So what comparators do basically, they have an input voltage. So basically at that particular amount of time, we have input signal, and what is the amplitude of that signal at that particular time. So let's say it is x. So if x, is it greater than 5 or not? If it is yes, then it will give 1. If it is not, then it will give 0. So we start from 1, and if it is greater than 1, then we have 1. If it is greater than 2, then we have high as output. If it is greater than 3, then we have high as output. So it is greater than 3, so it lies between this level, right? So until here we have high, but the comparator gives 0 when it is lesser than the case value. So then 1 1 1 0 0. So this is the digital word which will get assigned to that particular value at that particular time. So that's how we discretize amplitude. So that's how quantization happens for amplitude, but it is done parallelly. And this method is basically a dumb way to go, because when it comes to thousands of thresholds, so basically like we are using Node MCU, right, in our lab. So Node MCU has a 16-bit resolution, so it goes to 2 to the power 16 levels. So when it comes to that much of thresholds or bins, so we need basically 2 to the power 16 comparators, and that's very hard to implement on a system because it's very costly, it's very space consuming, and energy power consuming. So that's not a way to do that. Obviously, by some tricks and things, we can do it, because this kind of approach will give us the output very quickly. And this is basically used in flash ADCs, but we are trying to go for sigma delta modulation. So basically, when we talk about this kind of approach, so we need to trade off between expenses, cost, resolution, and component utilities, because so many components are used over here for higher speed basically. So example, let's say in a system where this kind of ADC is used in a feedback path. So in a feedback path, the delay leads to instability, and we have to minimize the delay. So there we cannot trade off this. So we have to use such kind of approach for higher speed. But then sampling is like so we will take an example. So sampling is a linear operation, but quantization is a non-linear operation. So sampling of time basically is linear operation, or it can be presented by a linear system or linear function. But quantization of data basically from continuous amplitude to digital amplitude is a non-linear function. And that's why if we say that we build a system where we first do sampling and then do quantization, and then whatever we get discrete output, we can feed it to the digital system. So it will not remain the same when we do discretization first of amplitude and then we'll do sampling of time. Then it will be something different. So the sequence matters, and we won't get the same behavior of the system if the sequence of these two is changed. So we will take an example, and that example is basically of a disk drive read channel. We have a hard disk, and there is a lot of data present in this hard disk. And basically, when it comes to telescopic level or very minute level, so it's basically a needle which is pointing towards north and south, giving us 1 or 0, and we have a head which is reading that data. So whatever the data is read by this head is basically very small. So we need voltage gain amplifier. Then after we amplify the voltage or the gain, we have filters in the sake to reduce noise and other factors. And then we pass the data to the analog to digital converter. And this timing part keeps control over it is done in a proper time or not. So that's how our system will look like, and we'll try to design this kind of system. So this was the way to quantize the amplitude. So another way to quantize is another way of quantization of amplitude can be by iterating the loop. So here we were doing the operation parallelly. So now what we'll do is we will use this comparator, but we will iterate through the levels. And uh, when we do it by iterating the loop by using same structure, here the component utility is minimized, resulting in trade-offs for speed in order to achieve high resolution. So such method of implementation is basically called sigma delta modulator, which we are going to look into. And coming back to sampling, so we would focus on minimal data loss, and enabling this minimal data loss is basically the theorem that tells us about sampling is derived from Nyquist theorem. So basically it says that if we have a signal with a bandwidth of B, so let's just first look at the definition. Let's say that we have a signal with bandwidth B, then we can reconstruct it perfectly in a discrete system as long as we sample it at a rate of higher than 2B. So the sampling rate, while sampling, we also talk about sampling rate. So we'll discuss it in detail when we will cover sampling topic. So while doing sampling, the sampling rate should be greater than the twice the bandwidth of the signal. Hence, we will first understand sampling mathematically, and then we will get to the circuit level, and then we will get to the characterization. Characterization is basically acknowledging all the non-idealities. So that's how our flow will be. And as we discussed, the tools which we will need is basically digital signal processing, analog circuit design, and physical devices or MOSFETs. Basically, we will need the physics of MOSFETs a little, and then we, for discussing or considering gain, stability, Bode plots, negative feedback, we will need the concepts of control theory. So these will be our tools. So as of now, if you have any questions, do let me know, or else we'll start with sampling.
Yeah, please, I have a question.
Yeah, please.
You said that we have a lot of small signals that we want to them to pass, yes? So here in this level we use a filter or amplifier.
Yeah,
Which one we
perfect.
should?
So here we have a system. So what we do is basically we need to design a system which will convert the data. So here the data which we will be reading is basically a super analog data. So it will be like very analog. But then this data will be having a voltage which will be very less. So it is very small signal which is analog in nature. But then what we have to do is first we have to amplify that signal. So we will use we will basically use op amps, or we will use the amplifying circuits which will provide it some voltage gain. So when it will be amplified with respect to voltage gain, so then what we will do is we don't just have a signal, right? We will also be having other noise along with signal when we are reading the signal. So our signal has particular frequency, right? So till that frequency, we will pass the whatever the input is. But regardless of other frequencies, we don't want that noise. So we will use filters over there to just to pick up the frequency, or let's say just to pick up our signal and surpass the noise, and then we will feed it to analog to digital converter, where we'll look the configuration for sigma delta modulator. So that's how our system will look like, and that's how we will do sampling and discretization of data into this block. So that's how it will be proceeded.
Yeah, thank you. And here, right, the up when you talk about you say when time is discreted,
Mhm.
I actually write down this kind of like they're like filters.
Yeah,
This
just a
five,
second. Just a second, Anya.
okay.
Yeah, please. Can you please repeat your question?
Yes, you choose like for example five samples, right? You say
Yeah.
for example I choose five samples.
Mhm.
So mm, from where did you say that for example if it is less than two, it considered as one, and it is like bigger than two, it considers as zero. Can you please again tell me, is had a formula or something that you
Over
can
here,
realize
right?
this? Yes, exactly.
Yeah, so basically what we are doing is we are using op-amp as a comparator over here, which functions,
Yeah.
we will also look into that when we'll design the system on circuit level. But then we have a configuration of op-amp where we use it as a comparator. So what it basically does is that we have our signal. So it compares that signal to a certain value, for example, 5 volts. So if it's greater than 5 volt, then it will give the output as 1, and if it's lesser than 5 volts, then it will give output as 0. So this example was just to demonstrate the logic. So there are so many components and so many steps while designing the system. This is just for the sake of explaining the logic that that's how we will go from continuous amplitude to discrete amplitude. But yeah, like we will also study op-amp as comparator while designing the system on circuit level.
Yeah, Dan, thank you so much.
Yeah, and this is just a brief overview, but we will discuss the whole process of building a system in great detail. Like we will cover each and every topic. So this was just an overview of what we are trying to achieve in the end. So that's how we will proceed, and these steps will be followed.
Rishi?
Yeah.
Yeah. So for sigma delta modulator,
Mhm.
we will convert the signal to digital signal in the loop, right?
In the loop, in what sense?
Okay. Can you show me that circuit
Yeah, we
diagram?
are talking about this kind of loop,
Yes,
right?
yes.
Okay. So
Feedback.
what? Yeah. So this is the concept of feedback again. So this is the
Hmm.
concept of negative feedback
Hmm.
loop. So it's not a
Okay.
loop, something we are talking about, but like this is a universal concept. Let's say you're driving a vehicle and you want to drive at 50 kilometer per hour. So this is your desired speed, right? So but to attain that desired speed, so let's say you are at 30 kilometer per hour, so you are driving with a speed of 30 and you want to go for 50. So what you'll do, you'll accelerate, right? But at the same time you will be also looking at the speedometer, that what is the speed. So you'll accelerate it, and when you will reach at 45 meter per kilometer per hour, then you'll reduce the acceleration, right? So whatever you're doing over here, so whatever system is working, so basically whatever action you are taking is based upon the difference of the actual speed which you are at right now and the desired speed which you want. So basically the action taken by the system, which is basically the acceleration, is totally dependent on how much difference is there between your actual speed and the desired speed. So the difference is large, then you'll accelerate for longer period of time or accelerate more, right? If the difference is very less, so you're about to reach 50, then you'll reduce the speed. So whatever the action you're taking or whatever the action your system is taking, it is basically the difference, right? So difference between the desired speed and the actual speed. So basically here is what we are getting, the actual thing which will be fed up, and here the difference will be taken, and the difference will be provided to the system, and the system will take actions based on that difference. So this is the concept of negative feedback loop. So that's how it works. So we'll also talk about that, and you can refer to these concepts in the playlist of analog IC design of mine. So there I have discussed it in great detail, but I think I answered your question.
Yeah, Rishi.
So
Thank
that's
you.
why we are using this feedback. So basically, this is a feedback.
Yeah, okay.
Fine. Any further questions you have? Like, please give me a thumbs up or let me know. Then I have to show one more thing.
Yeah, I guess we can move forward.